With each passing day, the mystery that surrounds the universe deepens and challenges the imagination of scientists, who seek to understand the enigmas behind two entities that, although with similar names, present realities that are as different as they are surprising. For many years, the scientific community has debated the existence and nature of dark matter and dark energy, two components that together represent the majority of the cosmos, even though our understanding of them is still far from complete. Dark matter, for example, was introduced to explain observed discrepancies in the orbital velocities of stars and galaxies. According to classical models, just as in our solar system, where more distant planets orbit more slowly, stars located on the outskirts of a galaxy should have slower speeds than those closer to the center. However, precise observations have revealed that many of these stars are moving at unexpectedly high speeds, suggesting that there is a quantity of unseen mass that exerts a gravitational influence, keeping them in orbit cohesively. This hidden mass, which does not emit light and does not interact electromagnetically, remained an enigma for decades, leading researchers to postulate that an invisible component was responsible for holding the galaxies together, ensuring that massive clusters stay together despite the forces that theoretically could disperse them. Simultaneously, the discovery of the acceleration in the expansion of the universe brought to light another equally intriguing dilemma: dark energy. Initially, calculations based on Hubble's law suggested that the speed at which galaxies move away from each other should decrease over time as the universe expands. However, subsequent measurements, enhanced by techniques that used standard candles, supernova explosions of similar brightness, revealed a completely opposite scenario. The further away the galaxies were, the faster they appeared to move away, indicating that the expansion of the universe is accelerating. This mysterious phenomenon led to the hypothesis that a form of energy, uniformly distributed throughout space, was exerting a repulsive effect, counteracting gravity, and causing the universe to expand at an accelerated rate. Although measurements suggest that dark energy represents the majority of the universe, its intensity is so faint that, to date, no modern technology has been able to detect it directly, leaving scientists faced with a question: is this energy a fundamental component of the cosmos or just an illusion created by quantum effects and variations in the flow of time? What makes this debate even more fascinating is the fact that the proposed explanations for dark matter and dark energy, although robust in many aspects, cannot encompass all astronomical observations. At a time when the standard cosmological model, known as LCDM, dominated the scientific landscape, recent evidence has begun to point to discrepancies that suggest a revision or even a radical transformation in the way we understand gravity and the dynamics of the universe. Some researchers propose that, on galactic scales, the laws of gravity may behave differently than predicted by Einstein, influenced by quantum fluctuations that alter the flow of time and, consequently, the movements of stars and galaxies. According to this view, what we interpret as the effects of dark energy would actually be a consequence of the fact that light coming from regions where time moves more slowly reaches us at an accelerated rate, creating the impression that the universe is expanding more quickly than it actually is. Furthermore, there are theories that suggest that neither dark matter nor dark energy would be necessary to explain the observed phenomena. Some scientists argue that if we rethink the mechanisms that govern gravitational interaction on larger scales, we might find alternative explanations for the clustering of galaxies and the anomalous velocities of stars. These innovative models, although they have not yet achieved consensus in the scientific community, open doors to a new understanding of the cosmos, in which established paradigms can be challenged and replaced by more comprehensive theories. In this context, the idea that we live in a homogeneous and isotropic universe where matter is distributed evenly on cosmic scales begins to lose strength in the face of the observation of colossal structures that extend over billions of light years and that demonstrate a surprisingly complex pattern of organization. At the heart of this investigation is the constant search for answers that can unify these diverse observations and offer a more complete portrait of reality. While baryonic matter, the matter that makes up stars, planets, and all the celestial bodies we can see, represents only a small fraction of the known universe, forces and entities that we cannot yet identify or directly measure are responsible for many of the dynamic behaviors we observe on astronomical scales. Thus, the scientific community finds itself facing a colossal challenge, unraveling the secrets of a universe that appears to be, simultaneously, behaving predictably and full of mysteries. This duality intrigues not only experts, but also anyone who looks up at the night sky and wonders about the true nature of reality. In short, the question of dark matter and dark energy continues to be one of the most exciting and controversial topics in modern cosmology. Evidence accumulated over decades indicates that something is, in fact, beyond what we can see and measure with our most sophisticated instruments. However, as new theories and models emerge, challenging established paradigms, the mystery deepens and questions multiply. What really makes up the universe? What fundamental laws govern the behaviors of particles and celestial bodies on such vast scales? Perhaps one day, the combination of technological advances and the theoretical boldness of scientists will reveal the hidden truth behind these enigmas, transforming our understanding of the cosmos and, consequently, our place within it. Until then, the debate remains open, fueling the imagination of researchers and inspiring future generations to look at the sky with the same fascination and thirst for knowledge that drove so many great discoverers throughout history.